It's in here.
Okay.
I thought with you, but he doesn't. Is that how I thought it was? I didn't know.
Okay, any questions on that last review assignment?
Yes,
What, Kate?
12 and 13.
12 and 13? Okay, did you watch the video?
The one that you sent out at like midnight last
Yeah.
night?
No, it
It
wasn't
wasn't
like,
like midnight.
Well,
like
I,
2.
I opened it, I saw it at midnight. I was in bed and I was like, so.
because they sent that out like yesterday afternoon.
Okay, well, I was at swim and then I did other homework. My bad.
Okay, I'm gonna go, good, it's okay, because actually 12 is very relevant to what we're gonna do today.
Cool.
Okay? So, here's the basis of today's lecture. And that's the difference between weak acids and strong acids. Okay? Now, here's the deal. You actually have to go back to the definitions of acids and bases. So, kind of the first working definition of acids and bases was what's known as the Arrhenius definition. So, this is what I refer to as like the Chem 1 definition of acids and bases. So, acids are going to contain hydronium ions like hydrochloric acid, nitric acid, sulfuric acid, hydrobromin. And don't forget, okay, by Monday, when you all are in here for that quiz, you need to know at least 4 of the strong acids and their formulas, okay? At least 4. I'm going to say, I don't care which ones you pick, but you're going to pick 4, and you're going to write down the names, and you're going to write down the formulas of it, okay? So I'm going to tell you straight up, that's going to be the last question on the quiz on Monday. Name 4 of the strong acids, write down the formulas, write down the names. Well, hydrochloric acid, that's a gimme. Okay, y'all have been dealing with HCl since Chem 1. So, and bases are going to be sodium hydroxides, lithium hydroxides, strontium hydroxides. So, acids have hydroniums, bases have OHs. And whenever these two are neutralized, when you have like HCl and sodium hydroxide, you're always going to get water and the salt from it. Okay, so whenever you neutralize these Arrhenius acids and bases, you always get water and a salt. Okay? Generic way to look at it. And that was cool, and that lasted for quite a while. So this is like I said, this is the Chem 1 definition of acids and bases. Okay? Now, the more advanced one is what's known as the Bronsted-Lowry definition. Now, here's the significance in terms of when this came out. Okay, so the Bronsted-Lowry definition didn't come out until 1923, so less than 100 years ago. The reason that they had to wait until 1923 to come up with this, because these are defined as an acid donates a proton and bases accept a proton. The reason that you didn't have this before 1923 is because we didn't know protons, electrons, and neutrons existed. Okay? It wasn't until like around the early 1920s that we even found the subatomic particles to begin with. So you couldn't have had this definition prior to the discovery of those particles. So if you go and look at chemistry books prior to about 1920, and if you look at the index, there is no mention of protons, electrons, and neutrons. Okay, we didn't know they existed. So even like 100 years ago, in terms of science, in terms of humanity, this is a relatively new discovery. So, and you'll see that Bronsted-Lowry definition also works with the Arrhenius, but the Arrhenius doesn't work with Bronsted-Lowry. So, acids donate a proton, bases accept a proton. Okay, and remember, a hydronium ion is nothing but a proton, because a hydrogen atom would have a proton and an electron. You take away the electron, you only have a proton left. Okay? So don't flip out. A hydronium ion is the same thing as a proton. Okay? It's the exact same thing, because that's what it is. Okay. So, with that said, is something, and here's the difference between these two. You have weak acids and you have strong acids. So weak acids, when you put them with water, you only have a slight percentage that are going to ionize. So, and this is how this is written. You have HA, which is a generic form of an acid. It's a hydronium ion, and the A just stands for the anion. Okay, if this was like acetic acid, it would be HC2H3O2. If it was hydrochloric acid, it would be HF. So A is just a generic anion, it could be anything. And you put that in with water, and you form a hydronium ion and an anion. So the next 3 weeks, you are going to live and die by this right here. Okay? This is going to be your go-to bread and butter equation. This is what we're going to spend the next 3 weeks talking about. So if you look at the definition of a Bronsted-Lowry acid, so this HA is going to be the acid, okay? Because of the fact that it's going to donate a proton to the water. The water here is going to be the base because it's going to accept that proton. Now, remember, the only reason this works is because if you look at the molecular structure of water, water is H2O, it's got an oxygen, a couple of hydrogens, right? And it has a couple of unbound pairs of electrons, we'll get into that later. So it has this huge dome of negativity. So you have a very negative end of the water molecule, and then you have a positive end of the water molecule. So basically what happens is that this proton here is more attracted to the water than it is to itself. So if it's a strong acid, okay, if it's a strong acid, it ionizes and you end up over here, okay? This is how this thing is going to exist. Now, this is going to be relevant to today's lecture as well. When you deal with Bronsted-Lowry, you have what's called the conjugate acid and the conjugate base, okay? So in this situation, this H3O is what we call the conjugate acid, and this is the conjugate base. So here's how you can recognize this. Your conjugate acid, if you reverse this reaction, this would give up that proton to get back to being the water. This conjugate base would accept that proton and get back to being the acid. So on Bronsted-Lowry, you have an acid and a base, and then you also have a conjugate acid and a conjugate base. Okay? So if it's a weak acid, okay? If it's a weak acid, what that means is that very little of this forms. Okay? You don't have much of this at all. Might be 3-5%, very little of this. Okay? If it's a strong acid, it all goes over here. And that's the fundamental difference. So if you have a weak acid like acetic acid, like I talked about in the video yesterday, we're going to deal a lot with acetic acid because acetic acid is just vinegar. Okay, so it's pretty easy to use acetic acid, it's cheap. So if you were to look at an atomic level of a container of acetic acid, you would see the vast majority of it existing in the molecular form, where that proton is still attached to the anion. You would see very little of it over here as an ionized acid. Okay? Now, if it's a strong acid like hydrochloric acid, you would basically see none of it existing as HCl. And you would see it all existing like this. Okay? So that's the fundamental difference that you have to get straight. Now, you can apply this in terms of human interactions. Okay? So this is like a loving couple who's, oh, we're in love. Okay? Right? It's love, true love. And there's this very, very strong bond between them, okay? So if they ionize, like, oh honey, hey, I gotta, you know, go to the store, okay? They might be separated for a little bit, but given the opportunity, bam, they're gonna go back over here and they're gonna reform this, okay? So here's the dichotomy. If you have a weak acid, you actually have a strong bond between the anion and the base. Okay? So that's the dichotomy. The other thing that you talk about is the strength of the conjugate base or the strength of the conjugate acid. So here's where this plays out. I'm going to plant this seed. We'll talk more about it tomorrow. If something is a weak acid, what that means is that it has a strong conjugate base, okay? Now, if something is a strong conjugate base, that means that it's really sticky, okay, in terms of protons. So if you have a strong conjugate base, that means that it really wants to take that proton and reform that acid, okay? So if you apply this to humans, if a couple is a weak couple, okay, and here's the dichotomy. If you have a weak couple, that means that they actually have a very strong bond with each other. And that weak couple has a very, very strong conjugate base. So if they're separated, they don't like it. They want to go back to being a couple, all right? So imagine that you all go to prom. Let's assume that you guys get to have prom this year, okay, with masks and everything, okay? So let's say you get to have prom. And so there's this loving couple, right? And one of them goes to go, hey, I gotta go to the bathroom. Okay, so runs to the bathroom, boom, they're ionized, right? Totally, this is bad, right? So as soon as they get out, boom, they're back together, okay? So weak acids have strong conjugate bases, which means it wants to pull that proton back and reform this. Now, if it's a strong acid, so this is if it's a strong acid, you're going to prom, but we're just going as friends, okay? We're just friends, okay? That's it. So as soon as you get to prom, okay, here's this water molecule. So this is like your buddies, right? So here are your buddies, you show up to prom. You are more attracted to the water, to your buddies, than you are to your date. So as soon as you get to prom, you're going to completely ionize. But you're happier over here, okay? It's like, yeah, we went to prom together, but we're just going to hang out over here, okay? You might get together for a little bit again. Oh, maybe we'll go get a picture. Oh, snap, snap, picture taken. Okay, I'm going to go back and hang out with my buddies. So it boils down to a tug of war. If it's a weak acid, this proton is attracted to the water molecule. So if you're this loving couple, okay, if you're the weak couple, you show up at prom, and you see your buddies over there, right? And they're going, hey, come on, let's go hang out. And you're going, no, I got to stay with my date, okay? Because you have such a strong bond. But if it's a strong acid, you have a very weak attraction, okay? There's some, okay? There's some attraction, okay? But as soon as you see your buddies, bam, we're out of here. So if it's a strong acid, equilibrium is to the right. If it's a weak acid, equilibrium is to the left, okay? Now, here's how this plays out with rice charts, okay? So if you look at and you are going to live and die by rice charts, by the way. If you don't embrace this idea of rice charts, it's going to be a long 3 weeks. I'm going to tell you this right now. Number one, I'm not even going to grade your work if I don't see a rice chart, okay? I'm going to tell you this right now. Love y'all to death. If you don't keep this stuff organized where I can track it, I'm not grading it. I'm just telling you this right now. So if you look at what's happening on number 12, you have acetic acid, which is technically HC2H3O2, right? And you're going to have some water in there. And you have the potential to form H3O and the anion. Okay? All right? So here's the deal. So here's my reaction. Here's my rice chart. So we're going to actually look at two different rice charts. One where you have acetic acid, and then we're going to have another one where we have hydrochloric acid. Okay? So, acetic acid is like the poster child for weak acids. Okay, it's the absolute poster child. So, what's going to happen here is this is going to be 0.02 molar. This is going to be what these stand for. Here's your reaction, here's your initial set of conditions, here's your change, here's your equilibrium. So, this is going to be a situation where you have a Bronsted-Lowry acid base. This is acting as the acid. This is going to be your base. Here's your conjugate acid, here's your conjugate base. So, until we get into buffered solutions, which we will, okay, for now, you assume that these over here start as 0. Now, don't worry about the concentration of water, okay? Water isn't going to be a part of the story, okay? Because water is just water. So, if it's a weak acid, some of this is going to ionize, and this is the whole point. We don't know how much is going to ionize, but some of it is. So we go minus X, plus X, plus X. Now, the reason that these are X's over here and not two X's is because these are all in 1-to-1 ratios. Okay? These are all 1-to-1 ratios. So whatever I lose here is whatever I gain here. So if you go with like sandwiches, okay? So let's say that you have a sandwich that's a slice of bread and a slice of cheese. Okay? It's not a very exciting sandwich, but it's a sandwich. So you have a slice of bread and you have a slice of cheese. So let's say that you have 10 of those. Okay? You have sandwiches. Now, some of the sandwiches, and you're going to assume that you have no cheese and you have no bread. So if like 4 of the sandwiches come apart, then you would end up with 4 slices of cheese and 4 slices of bread. So whatever you lose over here is whatever you gain over here. So at equilibrium, this is 0.020 minus X, this is X, this is X. Now, I cannot emphasize this enough. This is at equilibrium. Now, this is what Mother Nature wants. Okay? Hard Mother Nature wants to be in equilibrium because that's when Mother Nature's chilled out. Okay? This is what she wants because that's the lowest energy well. Okay? Mother Nature wants to be at equilibrium. Like if I push this balloon over here and I let go of it, what's it going to do? It's going to go back down. Why? That's an equilibrium, right? If the balloon was in equilibrium here and I would let go of it, guess what? It would stay there. But it doesn't. It goes back down to this point of equilibrium. So that's what Mother Nature wants. Now, on your equation sheet, you have this Ka equals hydronium ions times your anion concentration divided by Hn. This is subtle, but this is the whole key to understanding this concept, is this equation right here. Anytime you see the letter K, that means you're at equilibrium. Now, in contrast to this, we're going to use the letter Q later on. Q means it might be at equilibrium, but we don't know. So Q is like we don't know, but it could be. K, definitely at equilibrium. Okay? So, when you look at your Ka values, so in the back of your textbook, on page 1090, you're going to use this a lot. So what this lists is all of the Ka, K1, K2, K3 values for all of these acids. Okay? Now, the reason that you have like columns of, hold on. That's actually on page 1092. My bad, 1092. It's the next page of 1092. So you've got K1, Ka1 values, K2 values, K3 values. Notice that most of these acids are what we call monoprotic, which means that they only have one proton. You get into like, for example, where's it at? Hydrogen sulfide, okay, which is H2S. Notice that it has two Ka values. One when you pull off the first proton, one when you pull off the second proton. Now it's rare, but if you get down here to phosphoric acid, which is H3PO4, notice that phosphoric acid actually has three K values. One when you pull off the first proton, when you pull off the second one, and then when you pull off the third one, okay? So that's rare that that happens because most acids are what we call monoprotic, meaning they only have one proton. But that's why those have different K values. So here's the deal. When you look at this in terms of being in equilibrium, if you look at acetic acid, and I gave you that Ka value, which was 1.8 times 10 to the negative fifth, what that means is that Mother Nature wants this number, okay? Winner, winner, chicken dinner. This is, if you have acetic acid, what Mother Nature wants to do is mathematically produce a value of 1.8 times 10 to the negative fifth, so that when you multiply the hydronium ion concentration times the anion concentration and divided by the acid concentration at equilibrium. Now listen to me. Here's the whole key to this. At equilibrium. This is what Mother Nature wants it to be. Now, through whatever combination is going to happen, this is when Mother Nature is most stable. That's when that balloon is at the bottom of the arc. And Mother Nature is going to do whatever it has to do to get to this point. Okay? So, in this situation, we know what the Ka value is. We went to the back of the book, oh, here's the Ka value of acetic acid. So what that means is that at equilibrium, my hydronium ion concentration, which is going to be X, and my anion concentration, which is going to be X, divided by my concentration of my acid, which is technically going to be 0.020 minus X. Now, here's the deal. Unless I explicitly tell you differently, don't worry about subtracting this X. And here's the reason why. Because then you have to solve it as a quadratic. Okay? Because then you've got to multiply Ka times 0.020 minus X. That's going to equal X squared. And then you've got a value in front of your X squared and a value in front of your X, and then you have a numeric value, and you have to solve it as a quadratic. Unless I explicitly tell you to do that, don't worry about it. It's what's known as the 5% rule. If your percent of ionization is less than 5%, what we're saying is that subtracting this X isn't going to change this number enough to make any difference. Okay? No, did you work it as a quadratic?
Yeah.
I told you that in the video, not to work it as a quadratic. Because you're sitting there going, oh, man, okay? It isn't bad. Your calculators probably do it for you. But here's the deal. Unless this is a big number, okay, this isn't going to change it. It's like taking a drop of water out of the ocean, okay? Technically, when you take a drop of water out of the ocean, the level drops, but it's not enough to worry about, okay? So the same thing is going to happen here. So but now today, on the assignment, there is going to be a problem where I tell you, you have to work this as a quadratic, okay? And I will tell you that. But unless I tell you, don't worry about it. So this is just going to go away. So here's the deal. So you know everything except X. This becomes X squared. So you have Ka times 0.02. Oh, screwed that whole thing up. Square root of all that, that's going to get you your X, which is, now here's what's important. When you get this X, that gets you two things. It gets you your hydronium ion concentration, and it gets you your anion concentration at the same time. So when you do this, you actually get two numbers. Now, the reason that we don't worry about the anion concentration is that we don't have any probes that can measure the anion concentration. But we have pH probes which can measure the hydronium ion concentration. So this is why we focus on the hydronium ion concentration, because we can measure that. We can't measure the anion concentration with our probes, but we figured, hey, if we got this, hey, we got that. Okay? That's the reason why. So, here's the deal. You can find Ka values for weak acids because the numbers on top are small and the numbers on the bottom are pretty big. Now, if you look on that chart, you'll notice that there's a wide change in the Ka values. Okay? So, if you look at how you're going to mathematically generate a Ka value, so if you have a small Ka value, what that means is that these numbers on top, your hydroniums and your anions, those are really, really small numbers. In other words, it doesn't ionize very much. And then you've got a big number down here. Now, if Ka is a smaller value, okay, that means that these numbers on top are bigger and the numbers down below are smaller. So when you look at how you get a Ka value, Ka is all about understanding mathematics. If you have a small Ka value, look at what happens mathematically. The numbers on top are small, the numbers on the bottom are big. If you have a bigger Ka value, you have bigger numbers on top, you have a smaller number on the bottom at equilibrium. Now, let's contrast that with hydrochloric acid. Now, if this is hydrochloric acid and water, you get hydronium ions and your anions. So let's say that's 0.02 molar, that's 0, that's 0. Now, here's the deal. If it's a strong acid, we don't write minus X. We know how much of that is going to ionize. We know that by definition of a strong acid, this is all going to ionize. Okay? It's all going to go away. That's going to be, all of it's going to ionize. Boom, it's gone. This is going to be 0.02. This is going to be 0.02. So that's 0, that's 0.02, that's 0.02. So if it's a strong acid, okay, if it's a strong acid, if you try and calculate a Ka value, here's why you don't have Ka values for strong acids. Because you would take 0.02 times 0.02 divided by 0. So as soon as you divide by 0, what's going to happen? It's undefined. Okay? It's an undefined value. You can't, so if you look down that chart, there are no Ka values for strong acids because they don't exist. Either they're undefined or this is a really small number. It might be like 0.0000001. Okay? You might have a little bit of it. It's going to be like 0.0000001, which makes this a really big number. So this is why I'm going to make you learn the strong acids and their names and their formulas. Because on the test, I don't want you to go, hey, Mr. Burkamp, I can't find the Ka of hydrochloric acid. And I'm going to go, for the love of God, did you not listen to a word that I said? So if you go down that list, there are no Ka values for strong acids, except for sulfuric acid, which is H2SO4, because that's a diprotic acid. So, and this is one of the questions on the assignment. So you can't find a Ka value for H2SO4 because it completely ionizes. But then when you get to HSO4 turning into SO4 minus and a hydronium ion, you can find a Ka value for this. So H2SO4 is a strong acid. HSO4 is a weak acid because of the fact that once you get this, it's kind of like, here's the analogy. If you look at H2SO4, So this is like mom and dad, and they've taken their twins, Timmy and Tommy, to the zoo, okay? Timmy's annoying. So they don't care if Timmy gets eaten by the lions. It's like, sorry Timmy, bummer, too bad, okay? They have no attraction for Timmy, so if Timmy gets ionized, or lionized in this case, they don't care, okay? They don't. Now, but now they've got Tommy left over. They kind of like Tommy. So they're going to kind of hold on to Tommy because it's going to be awkward when they get back home to Grandma and Grandpa's. What happened to the boys? Well, Timmy got lionized, okay? Tommy, we kind of felt a little bit of a moral obligation to hold on to him. So they do have an attraction for that proton that's left over. So that's why you can find a Ka value for HSO4, but you don't find one for H2SO4. Okay. Got that. Good. Okay. So, when you look at Ka values, you can only mathematically calculate Ka values for weak acids. They're not listed for strong acids. Okay. So did that answer your question on that one?
On that one, yeah.
Okay.
Kind of.
Kinda?
Well, I don't completely understand everything yet.
But you will. You'll get there. I've given you certainly enough information to answer it.
Yeah.
Okay, so we'll get back to 13 later.
Yeah.
Now, so one of the things you want to calculate on number 12 is the percentage of ionization. So your percent of ionization is going to be the concentration of your hydronium ions divided by the concentration of the acid. So on 13, if you go through, once you find X, okay, on 13, out of this calculation right here, you get 6.0 e to the negative fourth. Okay? So that's the concentration of your hydronium ions and the concentration of your anions at equilibrium when the concentration is 0.02. So that's the concentration of your anions and your hydronium ions. So to get your percent of ionization, you're going to take that 6.0 times 10 to the negative fourth, and you're going to divide that by the concentration of the acid, which is 0.02, and then multiply by 100. Okay? And typically what you'll find is that your percent of ionization for weak acids is a pretty small value. Now, obviously, the weaker the acid is, the smaller this number is, and the smaller the percentage of ionization. Okay? Okay?
What's the rice method?
Huh?
What's the rice method?
That's what I just did.
Yeah, I know, but how do you do it? Like, I saw you do it, I just don't know what you were doing.
Okay.
What does it stand for?
R is the reaction.
Okay.
I is the initial set of conditions.
Okay.
C is the change. And E is your equilibrium line.
Cool.
Cool? Okay. Y'all been sitting for a while. I forgot I printed some stuff out that I gotta go grab. So you all take a stretch, and I'm gonna be right back. Shut off that camera for a second.
Scores, fun and scores.
There's like redox reactions in chem, in biology.
Yeah,
Yeah.
photosynthesis.
Yeah, kind of is. Yeah.
Good biochar.
Yeah, but that's so cool. But don't talk about breaking bones and then having them regrow. That's where I draw the line. Okay?
Yeah, that's kind of cool.
If you look
No,
at
stop,
it
shut up.
if you look at it on a molecular level, it's kind of cool.
No. Okay. So here's where they had to come up with a different definition of acids and bases. So, and I'll show you this demo later. So, if you have ammonia gas, if you've ever smelled any cleaning solutions that have ammonia in it, it's a very, very strong, pungent odor. So, if you look at ammonia, which is NH3, and again, we'll talk about the structure of this whole thing later. So, ammonia is a nitrogen atom surrounded by 3 hydrogen atoms. And it has a lone pair of electrons up here, which gives it like a dipole moment. So, basically what happens is you take ammonia gas and you bubble it through hydrochloric acid. What will happen is that this hydronium ion right here because it's positively charged, will become attracted to this lone pair of electrons on the ammonium, and you'll form NH4 plus and Cl. So here's what's important. If you were monitoring the pH of this solution, you would actually see the pH go up because you would be decreasing the concentration of the hydronium ions as an acid because they're going to be bound up with this NH4Cl. So in this situation, you have the ammonium, right, which is acting as a base, and then you have this acting as the acid. So the NH4 is your conjugate acid, and that's going to be your conjugate base, okay? So this is a situation where you had a reaction that was taking place, and you had a base, but it wasn't the traditional one with the Arrhenius definition where you add a hydroxide. So you had a reaction taking place where you changed the pH of the solution, but there wasn't a hydroxide involved. So that's why they had to come up with another definition of acids and bases. Now, if you do the same thing with water, okay, and we'll do this. Ammonia, you'll see, is very soluble in water because water and ammonia have a very similar type structure, and it's this old adage that likes dissolve likes. So ammonia gas is actually very, very soluble in water because of the fact they both have these unbound pairs of electrons, so they really, really like each other. So what happens is that you have the ammonia, you bubble it in through water, and you're going to form ammonium ions. Now don't confuse ammonium with ammonia, okay? This is ammonium, NH4 That's ammonia, NH3. So what you're going to create out of this are hydroxide ions. So with this one, because you're generating hydroxide ions, this actually makes the pH go up. It turns the solution basic because you're creating these hydroxide ions. Now, here's the anomaly. Here's ammonia. It's still acting as the base. But here, water is acting as the acid because of the fact that it's donating a proton to the NH3. So because of that, the NH4, that's still your conjugate acid, and the hydroxide is your conjugate base. So water is said to be what we call amphoteric. So if you, I'll get back to this screen in just a second. But if you look at what happens here with, if you have hydrochloric acid and water, here, hydrochloric acid and water, the water acts as a base because of the fact that it's accepting that proton. So here, water acts as a base. When you get down here with ammonia, water acts as an acid. So water is said to be amphoteric. What that means is that depending upon the situation, water can act as an acid or water can act as a base. Okay, like in amphibians can live in, oh, here's a biology tie-in, right? Okay, so what do you know about amphibians?
They're land and water.
They're land and water. So water is amphoteric. It can be a base, it can be an acid, depending upon the situation. Okay? So, and that's actually pretty rare. That's another thing that makes water so unique is because it can be an acid or a base depending upon the reaction. So again, this is where you had to have another definition of acids and bases that didn't fit with your traditional, hydrochloric acid and sodium hydroxide kind of thing. That's why you needed a broader definition. Okay, so if you were to look at two acids, okay, so acid number 1 has a Ka value of 1.0 times 10 to the negative 4th. Acid number 2 has a Ka value of 1.0 times 10 to the negative 10th, okay? They're both weak acids, okay? And their ionization can be written like this, HA. Now, this is the shortcut way of writing the ionization, okay? This is the shortcut way. Technically, what happens is that this is actually taking place with water, and you're technically forming hydronium ions and anions. This is like the long, technically correct way to write it, but chemists, scientists in general tend to be lazy. Some people call it efficient, okay, whatever that may be. So most of the time, we're just going to write it like this. Hey, here's some generic acid. You're going to get hydronium ions and you get the anions. But it isn't, if you do this, keep in mind in this middle picture that there's actually water molecules involved. We just don't write them in there to shortcut the process. So it means the same thing. So here's the deal. So you have two Ka values. One's 1.0 times 10 to the negative fourth. One's 1.0 times 10 to the negative 10th. Okay? So here's the question. In both of those, you have a hydronium ion concentration divided by HA. So Amanda, here's my two Ka values. 1.0 times 10 to the negative fourth, 1.0 times 10 to the negative 10th. Okay? Which one of these is going to ionize more? Acid number 1 or acid number 2?
Acid number 1.
You say that with no confidence whatsoever.
Very little.
Your answer is right. Okay? But why is your answer right?
Because that one's bigger than the bottom one.
Yeah.
So H plus is bigger than.
Exactly. So look at what had to happen to generate this bigger value. The only way that you can generate this bigger value, and here's the dichotomy, because these are negative exponents, okay? These are negative exponents. So negative 4, okay, versus negative 10, don't look at this and go, oh, that's a bigger number because it has 10 to the 10th. No, this is the smaller number, okay? Because it's a negative exponent, it's 10 to the negative 10th. So 10 to the negative fourth is the bigger number. So the only way that can happen is if these hydronium and these anion concentration values here are bigger than they are to generate this one. Because this is just generating a 10 to the negative 10th. This is generating a value of 10 to the negative fourth. Now, let's say, okay, so I'm going to get out your calculator. So let's say that both of these initial concentrations are 0.1. Okay? Let's say they're both 0.1. So this is hopefully where this all makes sense. So the concentration of X when it ionizes is going to be the Ka times the concentration of the acid, which is 0.10. Okay? So this is going to be the same for both of these. Because if you set up your rice chart, right? If you set up your rice chart, which I'm going to expect you to do, this is going to be 0, so here's your rice, okay? You're going to go minus X, plus X, plus X. That's 0.1, that's X, that's X. So here's your rice chart in action, okay? Here you go. So if I want to figure out what these are, then if you look at what that Ka value is, so that's going to be X squared divided by 0.1. Okay? Now, as long as these are non-buffered solutions, this process works every time. Okay? So, what I'm going to do is I'm going to take that Ka value, 1.0 times 10 to the negative fourth, multiply that by 0.1, and then take the square root of that. So, for this one, Amanda, what did you get X to equal?
0.00316.
So, give that to me in scientific notation, please, do.
3.16 times 10 to the negative
3.16 times 10 to the negative
third.
Okay. Now, let's do that same thing for this one. Okay? Take 0.1 times 1 times 10 to the negative 10th, and then take the square root of that.
I got 3.16 times 10 to the negative 6.
Times 10 to the negative 6th. Okay? Now, this is the concentration of your hydronium ions in both cases, right? So notice that this has a larger pH because it has a larger hydronium ion concentration, which means it ionized more. This one had a smaller concentration because it didn't ionize as much. So here's the deal. So this is going to make sense. You got to think it through though. This is the stronger, weaker acid. Okay? Okay, this is the stronger, weaker acid. This is the weaker acid. But here's the dichotomy. This one doesn't ionize as much because it has a stronger bond with the anion. This one ionizes more because that bond isn't as strong. Okay? So, this is the weaker acid, but it has the stronger conjugate base. So as soon as this thing separates, that anion goes, oh, come back here, oh, you can't leave, okay? So this doesn't ionize very, very much at all. So the weaker acid has the stronger conjugate base. The stronger weak acid has the weaker conjugate base. And that's what allows it to ionize more. Okay? So that makes sense. This is one of those areas you kind of have to mull it over a couple times, but then it kind of all makes sense. Okay, so let me hand out the assignment. I'll go over a couple of things on that. Okay. So let me go over okay. So the first half of this page is just a summary of everything that I just talked about. Okay? Here's your Ka calculation. Here's how you calculate percent of ionization. Here's your Rice chart. Take so you can what the letters are. Okay, so this is just a summary of what I've done. Now, Isaiah, you're the only kid that I haven't taught yet, so this is how I want assignments like this done. Number one, do not write. This is just like a page out of a textbook. Nothing gets answered on this sheet. Okay. So a lot of these are questions that you're just going to answer. So here's your paper, right? So on number one, you're going to say, like on this one, neutral solution to pH, what's the concentration of your hydronium ions, hydroxide ions, and the pH? So here's how I want this answered. So imagine that you come over here and you're going to draw a line down like this. So I want the answers here, and I want the work over here. Okay? So like on this one, on this one I want the hydronium ions, the hydroxide ions, and the pH. So you would say, okay, here's my hydronium ion concentration, it's going to equal something. Here's my hydroxide ion concentrations, here's the concentration, and here's my pH. What's that going to equal? Okay? So that's what I would want. I don't want to have to chase everything. Now, when you get to question number 2, that's something that you just have to write out. So when you answer question number 2, because that's like an explanation, you can write that across like this. You don't have to, if it's like a big explanation, you don't have to cram it in right here. You can, the things you have to write out, you can carry that across the page. So like when you get down to question number 9, okay? So on number 9, I've given you the acids and you want to write the conjugate bases, okay? So again, write these in, answer them in that sequence, okay? Now, because you guys are going to be taking, listen to me, you guys are going to be taking pictures of this on your phones. You have to have the charges on these. So when you're doing this, a lot of times when you're taking this, if it's like something really small and you don't write very dark, odds are it's not going to show up. So if you want to know what it should look like, okay, reference Amanda's assignments, because hers are really easy to grade. She likes dark, it's very legible. So if you're not sure if it's going to work, compare yours to Amanda. Now, again, I beg of you, this assignment is due tomorrow. So tomorrow, I'm going to go over any questions that people might have, okay? But before you send me that assignment, you look at that image on your phone when you take that picture of it. And if you can't read it, okay, and this is something that you have done, and if you can't read it, I promise you, I'm not going to be able to read it. Okay? So just keep that in mind because you'll be taking a picture of it. Now, you got to take your book home because there's questions out of the book that are on this back side. Okay? Now, when you get to question number 15.1, I'm going to tell you, you subtract the amount ionized to get the values in the equilibrium line. That'll make sense when you get to that problem. When you get to question number 62, which is that last one, you have to use the quadratic formula because it ionizes so much that when you subtract x, it becomes significant. Okay? That's the only one, Noah Hale, listen to me. That's the only one that you have to work as a quadratic. All the other ones, the subtraction of x is negligible. Okay? All right, so I'm done. If tomorrow you guys have specific questions that you want me to work, that you make, either email me or what's on the chat? Okay, all right. So anyway, so tomorrow if you have specific ones, you can either throw it into the chat on Zoom if you want to watch that, or email me, but that's the story. So I'm done. You got the rest of the time.